Good morning, everyone. Welcome to today's presentation. I'm excited to have you here. Today, we'll be exploring the fascinating topic of repair and rehabilitation of structures. As you can see on the slide, the course code is 21CE421T. Over the next few slides, we'll cover the key concepts, methods, and best practices involved in restoring and strengthening structures. I look forward to engaging with you all and sharing valuable insights. Let's get started. Welcome to the first unit, where we start with an introduction to maintenance. We'll explore the different facets of maintenance, including repair and rehabilitation, and understand why maintenance is so crucial. The role of a maintenance engineer is vital, especially when it comes to inspection and assessment procedures to evaluate damaged structures. We'll also look into the common causes of deterioration that can affect the longevity of structures. Moving on to the second unit, we'll delve into the strength and durability of concrete. Here, we focus on quality assurance, ensuring concrete meets standards for strength, durability, and thermal properties. We'll discuss common issues like cracking, their types, causes, and the effects climate and temperature have on concrete, along with corrosion mechanisms and how cover thickness plays a role. In the third unit, we explore various materials used for repair, including innovative options like polymer concrete, expansive cement, ferrocement, fiber-reinforced concrete, and even newer developments like geopolymer concrete and nanomaterials. The fourth unit covers techniques for repair and protection. We'll review non-destructive testing methods such as ultrasonic pulse velocity, rebound hammer, pull-out, and core tests. We'll also examine advanced repair techniques involving FRP, epoxy injections, shoring, underpinning, and corrosion protection methods like inhibitors, resistant steels, coatings, and cathodic protection. Finally, in the fifth unit, we focus on repair, rehabilitation, and retrofitting of structures. This includes strengthening techniques, repairing damage caused by corrosion, fire, leaks, or earthquakes, and using structural health monitoring with IoT. We'll also cover demolition techniques, including engineered demolition methods, and look at real-world case studies to tie everything together. Today, I want to highlight some key objectives related to concrete and structural durability. First, our goal is to help students gain a solid understanding of the quality aspects of concrete, including what affects its durability over time. We'll explore the common causes of deterioration that structures face, and how we can assess distressed structures to determine the extent of damage. Next, we'll look into the repair techniques used to restore damaged structures, which is crucial for extending their service life. Finally, we'll cover demolition procedures, understanding when and how structures are safely taken down when repairs aren't feasible. All of these points tie back to the overall theme of ensuring structural safety and longevity, which is essential in our field. So, by the end of this discussion, I hope you'll have a clearer picture of how these elements connect to maintain the integrity of our built environment. Now, moving on to the fourth unit, which focuses on techniques for repair and protection methods. In this section, we'll explore how to select the most appropriate repair techniques and protection strategies for different structural elements. It's crucial to understand that choosing the right method depends on factors like the type of deterioration, the material involved, and the structural requirements. We'll also discuss various protection methods that help extend the lifespan of structures and prevent future damage. This knowledge is key to ensuring that repairs are effective and durable, aligning with our overall goal of maintaining and preserving structural integrity over time. Let's dive into Slide 5, where we explore the crucial aspects of maintenance, repair, and rehabilitation. These are the facets that help us keep structures functional and safe over their lifespan. Maintenance, in particular, plays a vital role because it prevents deterioration and extends the service life of structures. The importance of maintenance cannot be overstated. Without it, even the best designed structures can quickly become unsafe or inefficient. This is where the role of the maintenance engineer comes into focus. They are responsible for various tasks, including conducting inspections, assessing the condition of structures, and deciding on necessary repairs. Inspection is a key part of this process. It involves systematically examining the structure to identify any damage or signs of deterioration. Following inspection, an assessment procedure is carried out to evaluate the extent of damage or deterioration, which helps determine the appropriate rehabilitation measures. Understanding the causes of deterioration is also essential. These causes can range from environmental factors like moisture and temperature changes to material fatigue or accidental damage. Recognizing these causes helps us not only repair current issues, but also prevent future problems. All these aspects are interconnected and vital for maintaining the safety, durability, and longevity of our structures, aligning with the overall goal of effective structural management. Now let's discuss maintenance, which is fundamentally preventive in nature. Essentially, maintenance involves activities like inspections and any work needed to keep the structure functioning as intended. The goal here is to identify issues early and prevent them from escalating into bigger problems. It's important to differentiate maintenance from rehabilitation. Rehabilitation focuses on restoring a structure to its previous service level, especially when it has been compromised or deteriorated over time. Think of maintenance as regular checkups to keep everything running smoothly, while rehabilitation is more like a comprehensive treatment to bring a structure back to full health. Both processes are crucial in ensuring the longevity and safety of our structures. Maintenance helps us catch small issues before they become costly repairs, and rehabilitation allows us to extend the life of existing structures when they've started to decline. Together, they form a balanced approach to structural management, aligning perfectly with our overall goal of sustainable and resilient infrastructure. When we talk about the life of a structure, improving its lifespan is absolutely crucial. A longer life period means we get a better return on our investment because the structure remains functional and safe for a longer time. Not only does this add value, but it also keeps the building looking good and aesthetically appealing, which is important for both users and visitors. Enhanced maintenance also means elements and components are easier to service. This makes it simpler to detect issues early, quicker detection of defects, so we can address problems before they develop into major deterioration. This proactive approach helps prevent serious issues like structural failure or even collapse. Safety is paramount, of course. Proper maintenance ensures the safety of everyone using the building, giving occupants peace of mind. It also fosters a feeling of confidence in the structure, that it's reliable and secure. All these points underscore the importance of maintenance. Regular, attentive maintenance isn't just about keeping things looking good. It's about ensuring safety, extending the lifespan, and protecting your investment over time. Let's take a closer look at some of the key building components that are essential for the overall functionality and longevity of a structure. First, we have the electrical wiring. This is the backbone of any building's electrical system, providing power to all the appliances, lighting, and devices. Proper installation and maintenance are crucial to ensure safety and efficiency. Next, plumbing systems are vital for water supply and sanitation. They include pipes and fixtures that deliver clean water and remove waste, playing a major role in health and hygiene. Moving on, finishes on floors and walls not only enhance the aesthetic appeal, but also protect surfaces from wear and tear. Choosing the right materials here is important for durability and maintenance. The roof terrace is another significant element, often used as an outdoor space or for additional functions like HVAC equipment placement. It requires careful design to prevent water leakage and withstand weather conditions. Lifts or elevators are key for accessibility, especially in multi-story buildings, and they need regular maintenance for safety and smooth operation. Doors, windows, and other elements like shutters or grills are not only about security and privacy, but also influence ventilation and natural light. Finally, we have building components that require ongoing maintenance. These are critical for preserving the integrity of the structure and ensuring safety over time. All these elements are interconnected and vital for the building's overall performance, safety, and longevity. Understanding each component helps us plan better and maintain our structures effectively over their life cycle. Let's talk about routine maintenance and how it helps us keep everything in good shape. Daily maintenance mainly involves cleaning, which might seem simple but is crucial for maintaining hygiene and appearance. Then, on a weekly basis, we focus on tasks like cleaning cobwebs, especially in those hard-to-reach corners, to prevent pests and keep the space tidy. Moving on to a monthly schedule, we check overhead tanks, doors, and windows. These are areas prone to dirt buildup or minor issues that, if neglected, could lead to bigger problems later. Annually, we undertake more comprehensive tasks, such as painting and attending to small repair works. This helps preserve the building's structural integrity and aesthetic appeal over time. And of course, we must be prepared for emergencies. Think fire outbreaks, floods, or cyclones. Emergency maintenance needs to be swift and effective to ensure everyone's safety and minimize damage. Understanding these different types of maintenance is key, because each plays an important role in the overall upkeep of a facility. Regular maintenance keeps everything running smoothly, prevents costly repairs, and ensures a safe and comfortable environment for everyone. Let's talk about some common deficiencies in design that can lead to building distress. One major issue is the poor detailing of reinforcement in reinforced concrete structural members and joints. When reinforcement isn't properly detailed, it weakens the overall structural integrity. Another critical point is the poor quality of construction, which can result from substandard materials or workmanship, ultimately compromising safety. Corrosion of reinforcement due to an aggressive environment is also a significant concern. When reinforcement starts to corrode, it reduces the strength of the structure and can cause cracking or even failure over time. Additionally, many structures have inadequacies in their structural system to effectively resist lateral forces generated by natural hazards like cyclones and earthquakes. If these forces aren't properly accounted for, the building becomes vulnerable. Settlement or differential settlement of the foundation is another factor that can cause distress. When the ground shifts unevenly, it puts stress on the structure. Lastly, extreme and unforeseen loading conditions, such as unexpected heavy loads or impacts, can also cause damage. All these points highlight how critical proper design, quality construction, and considering environmental forces are to ensuring the longevity and safety of buildings. They are the main causes behind many structural issues we see in buildings today. In this slide, we're focusing on the main objectives of a condition assessment for buildings. Essentially, the goal is to categorize the building into one of three groups based on its current state. First, we have Category A, where the building shows no signs of distress and meets all safety and serviceability standards as per the relevant codes. In such cases, no immediate action or retrofitting is necessary. Next, Category B involves buildings that are deficient or show signs of distress, but they're still repairable. These structures can be strengthened or repaired to meet safety requirements and performance criteria set by the user or the codes. Finally, Category C includes buildings that are severely damaged. These structures are in such poor condition that demolition is the best option, and often we consider rebuilding, sometimes even building back better than before. Overall, this classification helps us determine the appropriate course of action for each building, ensuring safety, compliance, and efficient use of resources. It's a critical step in the condition assessment process that guides our decision-making moving forward. Now, let's look at the main steps involved in the condition assessment. First, it's crucial to record any damage that may be present, whether visible or hidden, and to identify the causes behind any distress. This helps us understand what has happened and why. Next, we need to assess the extent of the distress, which involves evaluating how severe the damage is and estimating the residual strengths of various structural components, including the foundation and the entire system. This step is vital for understanding the remaining capacity of the building. Finally, based on this assessment, we can plan the necessary rehabilitation, retrofitting, or strengthening measures to ensure the building's safety and functionality. These steps form the core of a thorough condition assessment, guiding us toward appropriate repair strategies and helping us connect the dots between damage, cause, and corrective action. Let's start with the physical inspection of the damaged structure. This step is crucial because it allows us to visually assess the extent of the damage firsthand. We carefully examine the structure, looking for cracks, deformations, or any signs of distress. Next, we move on to the preparation and documentation of damages. It's essential to record every detail accurately, as these records will guide our analysis and help track changes over time. Collecting samples for tests is another key component. These samples, whether of concrete, steel, or soil, provide vital information about the material properties and any deterioration that may have occurred. Alongside this, studying relevant documents, including structural plans and previous inspection reports, helps us understand the original design and any modifications. Estimating the loads acting on the structure is also fundamental. Knowing the forces and stresses involved allows us to identify potential weaknesses. We also need to consider soil-structure interaction, which looks at how the foundation and surrounding soil influence the structure's behavior. Then comes the diagnosis phase. This is where we analyze all the gathered information to identify the root causes of the damage. Based on this diagnosis, we can determine the appropriate preventive steps to avoid further deterioration or failure. It's important to confirm the diagnosis through additional testing or analysis, ensuring our conclusions are accurate. Finally, we follow a thorough assessment procedure for evaluating the damaged structure, integrating all these aspects to develop a comprehensive understanding and plan for repair or reinforcement. All these steps are interconnected and essential for a reliable evaluation that supports the safety and longevity of the structure. Now, let's look at the estimation of future use and the steps involved in ensuring the structure's longevity. First, we consider remedial measures to strengthen and repair the structure. This is a crucial step to address any existing issues and enhance its overall stability. Once the repairs are completed, we conduct a post-repair evaluation through various tests to verify the effectiveness of the measures taken. One of the key tests we perform is the load test, which helps us study the behavior of the structure under simulated or actual load conditions. This gives us valuable insights into its performance and safety margins. Based on these findings, we then determine the appropriate course of action for restoring the structure to its desired condition. And as we move forward, these continuous assessments and evaluations are essential to ensure that the structure remains safe, functional, and durable for future use. Let's take a closer look at this slide. Here, I want to emphasize the importance of understanding the key points thoroughly, but in a way that feels conversational. As we discuss, I'll highlight the most critical concepts so they stand out clearly. It's essential to connect these points back to the overall theme of our presentation, showing how each piece fits into the bigger picture. Remember, the goal is to make these ideas not only clear but also engaging, helping us see their relevance and application. So, as we go through this, keep in mind how these insights build on what we've covered so far and set the stage for what's coming next. Stress in the component can be caused by external forces such as dead loads, which are the permanent weights of the structure itself, and live loads, like the weight of people, furniture, or equipment that can vary over time. Wind or seismic loads also play a significant role, especially in areas prone to earthquakes or strong winds. Additionally, foundation settlements, which occur when the ground beneath a structure shifts or compresses, can introduce stress as well. On the other hand, stress can also be induced internally within the structure due to factors like thermal movement, where temperature changes cause materials to expand or contract, or moisture changes that affect material properties. Chemical actions, such as corrosion or other reactions, can weaken materials and lead to internal stresses. Understanding these causes is crucial because they directly impact the deterioration of structures over time. Recognizing whether stresses come from external forces or internal changes helps us better predict potential issues and plan maintenance or reinforcement accordingly. This awareness ties into our overall theme of ensuring the longevity and safety of our structures by managing and mitigating these various stress factors effectively. Now, let's talk about the causes of deterioration, starting with design and construction flows. The way we design concrete structures really influences how they perform over time. If a concrete structure is well designed and carefully detailed, it will generally show less deterioration compared to one that's poorly designed, even if both are in similar conditions. One area to pay close attention to is the beam column joints. These joints are particularly vulnerable to defects, especially if the reinforcement isn't placed or detailed properly. Poor detailing and placement can lead to issues that accelerate deterioration, so thorough design and meticulous construction practices are essential to ensure longevity and durability. This connects back to the overall theme, emphasizing that good design isn't just about aesthetics or initial strength. It's about ensuring the structure can withstand the test of time with minimal deterioration. Let's talk about the environmental effects on concrete. Microcracks that form within the concrete are more than just tiny imperfections. They actually serve as entry points for moisture and atmospheric carbon dioxide. When these substances penetrate the concrete, they can cause significant damage, especially to the reinforcement steel inside. The moisture facilitates corrosion, and the carbon dioxide reacts with the concrete ingredients, further weakening the structure. In environments where conditions are more aggressive, think areas with high humidity, salt exposure, or pollution, the deterioration process accelerates. As a result, the concrete structures in these harsh environments tend to degrade faster, and their overall strength and lifespan can be severely compromised. This underscores the importance of understanding environmental effects because they directly impact the durability and longevity of our concrete structures. Recognizing these factors helps us design better, more resilient construction that can withstand such adverse conditions over time. Let's start with the importance of using good quality materials in construction. It's essential to ensure that the materials meet the standards set by IS codes through various tests. Using poor quality materials can lead to early deterioration of the structure. For instance, alkali aggregate and sulfate attacks are common issues that can cause the concrete to weaken prematurely. Additionally, if the fine aggregates contain clay or other impurities, they can weaken the bond between mortar and aggregate, ultimately reducing the overall strength of the structure. Moving on to supervision, proper oversight during construction is crucial. The work must be carried out strictly according to the specifications provided. One key aspect is adhering to the correct water-cement ratio, as this directly influences the strength, permeability, and durability of the concrete. Too little vibration can leave the concrete porous and honeycombed, which compromises its integrity. On the other hand, excessive vibration can cause segregation, where the components of the mix separate, leading to weak spots. These points highlight that quality control, from materials to supervision, is fundamental to building durable and safe structures. When we focus on these aspects, we're ensuring the longevity and resilience of our constructions, fitting into the larger goal of creating safe, reliable infrastructure. Now, let's talk about deterioration caused by corrosion. One of the most noticeable signs is spalling of the concrete cover, which happens when the outer layer peels off or flakes away. You'll also see cracks running parallel to the reinforcement bars, indicating internal stresses. Spalling often occurs at the edges of the structure, where the concrete is more exposed to environmental factors. Another key point is swelling of the concrete, which is a result of the corrosion process causing expansion inside the material. This swelling can lead to dislocation, or movement, of the concrete and reinforcement. Recognizing these signs early is crucial because they directly impact the structural integrity and safety of the structure. Corrosion-induced deterioration is a major concern in maintaining the durability of concrete structures over time. Now, let's take a closer look at how distress can be broadly classified. Essentially, we can divide it into two main categories: structural and non-structural. Structural distress refers to issues that affect the physical integrity of a building or structure, such as cracks in the walls or foundation problems. Non-structural distress, on the other hand, involves elements that don't compromise the overall safety, but can still cause inconvenience or damage, like interior cracks or cosmetic issues. Another important distinction is whether the distress is active or dormant. An active distress is one that's currently progressing or worsening, indicating that immediate attention might be needed. Dormant distress, however, is stable at the moment but could become active under certain conditions. Understanding these classifications helps us better diagnose and prioritize repairs, ensuring safety and longevity in our structures. It's all about recognizing the nature of the problem so we can address it properly within the broader context of structural health management. Today, I want to talk about structural distresses, which are issues that arise due to incorrect design. These problems often stem from faulty construction practices or overloading the structure beyond its intended capacity. It's important to understand that such distresses can pose serious safety risks to a building and its occupants. For example, extensive cracking of a reinforced cement concrete, or RCC, beam is a clear sign of structural cracking. Recognizing these signs early is crucial because they indicate that the structure might be compromised, and addressing these issues is vital for maintaining safety and integrity. So, when we talk about structural distresses, we're focusing on problems that directly threaten the stability of the building because of how it was initially designed or constructed. Let's take a closer look at this slide. Here, you can see the diagonal cracks that have developed in the beam. These cracks are significant because they often indicate that the structure is experiencing stresses beyond its intended capacity. When cracks form diagonally, it usually points to shear failure, which is a critical failure mode in structural elements. Additionally, notice the failure at the top of the column. This suggests that the load transfer from the beam to the column has been compromised. The failure at this connection can lead to a cascade effect, weakening the overall stability of the structure. Connecting this to our overall theme, these failure modes highlight the importance of proper design and reinforcement. Recognizing such crack patterns early can help prevent catastrophic failures. It's a reminder that understanding how loads are distributed and how elements respond under stress is key to ensuring safety and durability in our structures. Now, let's take a closer look at column failure, specifically focusing on buckling of the longitudinal bars. When columns are subjected to axial loads, one common failure mode is buckling, which can occur in the longitudinal reinforcement bars. This is particularly critical because these bars are responsible for carrying the axial load along the length of the column. If they buckle, the entire column's stability is compromised. Buckling happens when the compressive stress in these bars exceeds a certain critical value, causing them to bend or deform laterally. This deformation weakens the overall load-carrying capacity of the column. It's important to recognize that the failure might not always be due to crushing of concrete, but can also result from this buckling of the reinforcement. Understanding this failure mode helps us design more resilient columns. By properly detailing the longitudinal bars, such as ensuring adequate confinement and proper spacing, we can help prevent buckling and improve the overall stability of our structures. This concept ties back to the overall theme of ensuring safety and durability in our structural designs. Let's talk about non-structural distress, which is primarily caused by internally induced stresses within building materials. These stresses don't usually lead to the weakening of the overall structure directly. However, over time, some non-structural cracks can develop. When moisture penetrates through these cracks, or when weathering actions occur, they can cause more serious problems like corrosion of the reinforcement. This corrosion can compromise the safety of the structure, making it unsafe. So, while non-structural distress might seem minor at first, it's important to monitor and address it to prevent long-term issues that could affect the building's integrity. Now, let's take a closer look at cracks in good quality brick walls. Even with high-quality bricks and proper construction, cracks can develop over time. These cracks often indicate underlying issues that need attention. They might be caused by settlement, temperature changes, or even minor shifts in the foundation. It's important to understand that not all cracks are necessarily a sign of structural failure, but they should never be ignored. By inspecting these cracks carefully, we can determine whether they are superficial or if they point to more serious problems. Recognizing the key differences helps us make informed decisions about repairs and maintenance. This ties into our overall theme of building durability and proactive upkeep, ensuring that even the best materials are maintained properly to prevent bigger issues down the line. A crack is considered active if it is still in progress. That is, if the crack is still developing or growing. To determine this, we can fill the crack with mortar and then observe what happens over time. If the crack reappears after filling, it indicates that the crack is still live or active, meaning it will likely increase further. So, understanding whether a crack is active or dormant is crucial for assessing structural integrity. Active cracks suggest ongoing movement, whereas dormant cracks are stable and not likely to worsen. This distinction helps us decide whether repairs are urgent or can be scheduled later. Keep in mind, continuous monitoring is key to managing these conditions effectively. A dormant crack is one that, once it forms, remains static over time. It doesn't change or grow, no matter what happens around it. The key point here is that these cracks are essentially sleeping. They're there, but they don't evolve or worsen unless something else triggers a change. Understanding this helps us distinguish between cracks that are active and potentially problematic and those that are dormant and stable. Recognizing dormant cracks is important because they might not require immediate intervention, but we still need to monitor them over time as part of our overall assessment. So, in the bigger picture, knowing whether a crack is dormant or active is crucial for making informed decisions about maintenance and safety. Now, let's look at the 3 basic symptoms in concrete that indicate potential issues. First, we have cracking, which is quite common and can occur for various reasons like shrinkage, temperature changes, or structural stress. It's important to observe the type and pattern of cracks because they can tell us a lot about the underlying problem. Next is spalling, which involves the surface of the concrete breaking or flacking off. This often results from freeze-thaw cycles, corrosion of reinforcement, or poor mixing. Spalling not only affects the appearance, but also the durability of the structure. Finally, we have disintegration, which is the complete breakdown of the concrete material. This is usually a sign of severe deterioration, often caused by chemical attacks or long-term exposure to aggressive environments. These symptoms are key indicators of concrete defects and help us assess the health and safety of the structure. Recognizing these signs early allows for timely maintenance and repair, ensuring the longevity and integrity of our concrete structures. Let's take a closer look at corrosion in reinforced concrete beams and columns. As you know, these structural elements are vital for supporting loads and maintaining building integrity. However, corrosion of the reinforcing steel is a common and serious issue that can compromise their strength and durability over time. When the steel inside the concrete starts to corrode, it produces rust, which expands and creates internal pressure. This pressure can cause cracking and spalling of the concrete surface. You'll often see this as rust stains or flaky concrete on the surface. It's important to understand that corrosion not only weakens the steel, but also affects the overall stability of the structure. In beams, this can lead to reduced load-carrying capacity and potential failure under stress. In columns, it can cause instability and even collapse if left unaddressed. Preventing corrosion involves proper material selection, adequate concrete cover, and protective coatings. Regular inspections are also key to detecting early signs of deterioration. In the context of our overall discussion on structural durability, managing corrosion is crucial for extending the lifespan of concrete structures and ensuring safety. So, understanding these mechanisms helps us develop better maintenance and repair strategies. Let's talk about dampness, which is a common issue that can seriously affect the integrity of a building. When moisture seeps into walls or surfaces, it often leads to condensation, where humid air cools and releases water droplets. This not only looks unappealing, but can also promote mold growth. Another sign to watch for is efflorescence, that white, powdery residue that appears on masonry surfaces when salts are brought to the surface by moisture. Dampness can also cause structural and surface cracks, weakening the building's stability over time. Vegetation growth, like moss or weeds, can indicate persistent damp conditions and can further damage surfaces if not addressed. When it comes to masonry structures, any defects, such as cracks, loose mortar, or damaged bricks, can be both a sign and a cause of moisture problems. These issues often exacerbate dampness, creating a cycle that can be tough to break without proper maintenance. Overall, understanding these signs helps us identify moisture-related issues early, so we can take steps to preserve the building's strength and appearance. Dampness is a common issue that can significantly affect the integrity of a building. When moisture is present, it can lead to a range of problems, from structural damage to health concerns like mold growth. It's important to understand that dampness isn't just about visible water. It can also be hidden within walls or foundations. Addressing dampness early is key to preventing more serious issues down the line. This ties into the overall theme of building maintenance and ensuring a safe, healthy environment. By keeping moisture levels in check, we can protect both the structure and the occupants. Let's talk about condensation. This is a crucial process because it's all about how vapor turns back into liquid. When the air cools down to its dew point, the water vapor condenses into tiny droplets, forming clouds or dew. This process is key in the water cycle, helping to move water from the atmosphere back to the Earth's surface. Understanding condensation helps us grasp how weather patterns develop and why we see fog or dew in the mornings. It also ties into the bigger picture of climate and atmospheric science, showing the dynamic relationship between temperature, humidity, and phase changes. So, condensation isn't just a simple change of state, it's a fundamental part of Earth's natural systems. Let's talk about efflorescence. This is a common issue that appears as a white, powdery deposit on the surface of masonry or concrete. It happens when water moves through the material, dissolving soluble salts inside. As the water evaporates on the surface, these salts are left behind, creating that characteristic white coating. Efflorescence might seem harmless at first, but it can indicate underlying moisture problems that could lead to more serious structural issues over time. It's important to identify the source of the moisture and address it to prevent recurring problems. In the context of building maintenance and preservation, understanding efflorescence helps us assess the health of a structure and plan appropriate interventions. While it can often be cleaned off, preventing its return is key, which means managing water infiltration and improving drainage are vital steps. Overall, recognizing and addressing efflorescence fits into our broader goal of maintaining durable, stable, and aesthetically pleasing structures. Let's take a closer look at vegetation. Vegetation plays a crucial role in shaping our environment, influencing everything from climate to biodiversity. It includes all types of plant life, from forests and grasslands to shrubs and even algae. Vegetation helps regulate temperature, retain moisture, and provide habitats for countless species. It's also vital for human life, offering resources like food, medicine, and materials. When we consider environmental health, the state of vegetation is a key indicator of ecosystem stability and resilience. Throughout this presentation, we've seen how vegetation interacts with other elements of our environment, making it a fundamental component of the overall system. Understanding its dynamics helps us better appreciate the delicate balance we need to maintain for a sustainable future. Dampness in a building can often be traced back to various issues related to the structure itself. For example, leakage from a defective roofing system is a common culprit, allowing water to seep in during rains. Porous bricks also contribute because they absorb moisture, which then travels into the walls. Vegetation growth on walls can hold moisture against the surface, exacerbating dampness. When earth is used as backing against masonry, it can retain moisture and transfer it to the wall if not properly protected. Cavities and holes left during construction create pathways for water infiltration, compromising the wall's integrity. Improperly laid mortar joints can allow water to penetrate, especially during heavy rains. A defective damp-proof course fails to act as a barrier against rising damp, which is a major cause of dampness. Splashing rain off the ground onto the wall can also introduce moisture, especially if the ground level is too high or poorly finished. Defective window sills may allow water ingress during storms or rain. Pipes embedded within masonry, if not properly sealed, can leak and cause localized damp patches. Additionally, the presence of salt in mortar can lead to salt efflorescence, which attracts moisture and worsens dampness issues. Overall, these points highlight how structural and construction flaws are key contributors to dampness in buildings. Let's take a closer look at some common surface defects that can occur in construction and finishing. First, we have blistering, which appears as bubbles or bulges on the surface, often caused by trapped air or moisture. Next is bond failure, where the coating or plaster no longer adheres properly, leading to peeling or flacking. Cracking is another typical issue. These are fractures that can develop due to structural movement or material stress. Crazing refers to fine, interconnected cracks, usually on glazed surfaces or paints, giving a web-like appearance. Efflorescence is a white, powdery deposit on surfaces, resulting from soluble salts migrating to the surface with moisture. Irregularity of surface points to unevenness or roughness, which can be due to improper finishing or underlying issues. Recurrent surface dampness indicates persistent moisture problems, possibly from leaks or poor drainage, causing ongoing surface issues. Finally, we also see defects related to plastering and repair work. These can include uneven patches, poor bonding, or areas that haven't been properly finished. Recognizing these defects early is crucial because they not only affect the aesthetic appeal, but can also compromise the durability of the structure. Addressing these issues effectively helps maintain the integrity and longevity of our projects. Today, I want to focus on the term blistering. When we describe something as blistering, we're often talking about an intense, rapid, and sometimes overwhelming process or performance. It can refer to speed, heat, or even a kind of fiery energy that's hard to ignore. In our context, think of it as describing a situation or a performance that's moving so fast and with such force that it almost feels like it's burning through obstacles. This concept is important because it highlights the need for agility and resilience in our strategies. By understanding what blistering signifies, we can better appreciate how to approach challenges with a mindset that's ready to adapt quickly and perform at a high level. It ties back to our overall theme of pushing boundaries and staying ahead in a competitive environment. So, in essence, blistering captures that sense of unstoppable momentum, something that's powerful, fast, and transformative. Now, let's discuss some common defects that can occur in steel structures. First, rusting, which is a corrosion process that weakens the material over time. Then, we have excessive deflections, where parts of the structure bend or sway more than they should, potentially compromising stability. Buckling and bending are also critical issues. Buckling happens when compression members suddenly deform outward, while bending involves the gradual curvature under load. Twisting or torsion can occur when forces cause the structure to rotate or twist out of shape. Lateral bending is another concern, where the structure bends sideways, often due to uneven loads or forces. Moving on, we also need to be aware of defects in welds. These include shearing, which is a failure along a plane within the weld, bearing failure, where the weld can't support the load it's designed to carry, and tearing failure, which occurs when the weld material itself rips or tears under stress. Recognizing these defects is crucial because they can significantly impact the safety and longevity of steel structures. Overall, understanding these potential issues helps us design, inspect, and maintain steel structures more effectively, ensuring they remain safe and durable over time. Let's take a closer look at rust in Tor steel. As you know, Tor steel is widely used in reinforced concrete structures because of its high tensile strength. However, one of the biggest challenges we face is corrosion, or rust formation, which can significantly compromise the integrity of the structure. Rust occurs when the steel is exposed to moisture and oxygen over time, leading to oxidation. This process not only weakens the steel itself, but also causes expansion, which can crack the surrounding concrete. Understanding the behavior of rust in Tor steel is crucial because it directly impacts the durability and safety of structures. For example, excessive rust can lead to delamination or failure of the reinforcement, elevating the risk of structural collapse. That's why during design and maintenance, we need to consider protective measures like coatings, corrosion inhibitors, or even using more corrosion-resistant materials. So, in the context of overall structural durability, managing rust in Tor steel is a key aspect that ensures long-term performance and safety of our constructions. Now, let's take a closer look at some occurrences that are incidental to the construction stage. These are factors that can contribute to deterioration if not properly managed. First, we have the local settlement of the subgrade, which happens when the ground underneath the structure compresses or shifts slightly. This can lead to uneven support and potential cracks. Next, there's the movement of formwork, which occurs when the temporary molds shift or settle before the concrete cures fully. This movement can cause surface imperfections or misaligned elements. Then we have vibrations, which can be caused by nearby construction activities or equipment. Excessive vibrations can lead to internal stress within the structure. Internal settlement of concrete suspension, another point, refers to the slight sinking or shifting of the mixed concrete before it fully hardens, potentially leading to uneven surfaces. Settling shrinkage is also a concern. As concrete loses moisture, it contracts, which can cause cracking if not properly controlled. Lastly, premature removal of forms is a critical issue. Removing forms too early before the concrete has gained sufficient strength can lead to deformation or surface damage. All these factors are causes of deterioration that need careful attention during construction to ensure the longevity and durability of the structure. This slide highlights some common reasons behind certain structural issues or material behaviors in buildings. One key factor is the difference in temperature between the inside of the building and its external environment. When the temperature outside fluctuates, it can cause expansion or contraction in the building materials, which may lead to stresses or cracks over time. Another important point is the variation in internal temperature within the building itself. Different areas might experience different temperatures, especially if there are poor insulation or heating issues, leading to uneven stresses in the structure. We also need to consider drying shrinkage, which occurs as materials like concrete or wood lose moisture and contract. This process can cause dimensional changes and potential cracking if not properly managed. Lastly, temperature stresses are a critical aspect. These are stresses that develop due to temperature changes, again causing expansion or contraction. Understanding these factors helps us design and maintain buildings better to prevent damage and ensure longevity. Ultimately, recognizing these causes allows us to anticipate and mitigate potential problems in our structures. This slide highlights some of the common issues that can arise in bridge structures, and it's important to understand how these can impact overall performance. First, leakage through joints can be a significant problem, especially if joints are not properly sealed. This can lead to water ingress, which may cause deterioration over time. Next, inadequate drainage is another concern. If the drainage system isn't designed or maintained properly, water can accumulate, leading to increased stresses and potential damage. In addition, insufficient drainage slopes can contribute to water pooling, which again affects the longevity of the structure. Moving on, unanticipated shear stress in piers, columns, and abutments can occur when loads are not accurately accounted for, leading to unexpected failures or deformations. Material incompatibility within different sections of the structure is also a critical point. Using materials that don't perform well together can cause issues like cracking or delamination over time. Lastly, deflections are another key point. Excessive or unexpected movements can compromise structural integrity or lead to discomfort for users. Overall, these issues underscore the importance of meticulous design, proper material selection, and regular maintenance to ensure the safety and durability of bridge structures. When we look at failures in structures, there are several common causes that we need to understand. One major factor is errors in design, which can lead to vulnerabilities that might not be apparent at first glance. Additionally, mistakes made during earlier repairs can also compromise the integrity of a structure over time. Overloading is another critical issue. When a structure bears more weight than it was designed to handle, it can lead to failure. External influences play a significant role too. Natural events such as earthquakes, for example, can cause immense stress on buildings. Wind forces, especially during storms, can exert lateral pressure. Fire and tornadoes are also destructive forces that can weaken or destroy structures. Cyclones, flash floods, and other extreme weather conditions further add to these challenges, often pushing structures beyond their limits. Neglect in design is a silent but serious problem. When proper planning and safety considerations are overlooked, the risk of failure increases substantially. All these factors emphasize the importance of thorough, careful design and ongoing maintenance, especially when we consider the overall theme of structural safety and resilience. Now, let's take a look at some of the common causes of deterioration in reinforced concrete structures. One of the key issues is corrosion of the reinforcing bars, which often occurs due to carbonation of the concrete. When carbonation happens, it reduces the pH level of the concrete, making the environment around the steel more acidic, and this accelerates the corrosion process. Another major factor is sulfate attack. Sulfates present in soil or water can penetrate the concrete and react with the components, leading to expansion and cracking. This kind of chemical attack can significantly compromise the integrity of the structure over time. We also need to consider alkali-silica reaction, or ASR. This occurs when reactive silica in the aggregate reacts with the alkali hydroxides in the cement paste, forming a gel that swells as it absorbs water. This swelling induces internal stresses, resulting in cracking and overall deterioration. All of these issues are caused by aggressive, deteriorating chemical agents that attack the concrete and reinforcement. Recognizing these agents and understanding their effects is crucial for designing durable structures and implementing appropriate protective measures. This way, we can extend the lifespan and safety of our infrastructure. Now, let's look at slide 46, which focuses on how a passivating protective layer forms on steel surfaces. This layer is crucial because it helps prevent corrosion and extends the lifespan of reinforced concrete structures. Essentially, when steel is embedded in concrete, the environment plays a significant role in protecting it. The concrete cover acts as a barrier, shielding the steel reinforcement from aggressive elements like moisture and chlorides. This protection is not just passive. It involves the formation of a thin, stable, and adherent oxide layer on the steel's surface, which is known as passivation. This layer effectively prevents further corrosion reactions from taking place. The key point here is that the concrete cover provides an environment that encourages this passivation process, ensuring the steel remains protected over time. Overall, this slide highlights the importance of the concrete cover in environmental protection, working in tandem with the natural passivation process to safeguard steel reinforcement. This understanding is fundamental as we consider the durability and longevity of concrete structures exposed to various environmental conditions. Now, let's talk about depassivation of steel, which is a critical step in understanding reinforcement corrosion. When steel is embedded in concrete, it normally develops a protective passive layer that shields it from corrosion. However, this layer can be compromised under certain conditions. One of the main factors involved is oxygen. Oxygen is essential for the corrosion process to initiate, as it reacts with the steel once the passive layer is broken down. Another key element is water, but it's not just about having water present all the time. Instead, it's about intermittent presence, alternating wetting and drying cycles. These cycles can really accelerate corrosion because they cause fluctuations in the chemical environment around the steel, making it easier for corrosion to start and propagate. So, to summarize, the three elements needed for the initiation of reinforcement bar corrosion are oxygen, moisture, specifically in the form of these wet-dry cycles, and the breakdown of the passive layer on the steel's surface. Recognizing how these factors interact helps us better understand how corrosion begins and what we can do to prevent it, reinforcing the overall goal of durable and long-lasting concrete structures. Let's talk about carbonation. Carbonation refers to the process of dissolving carbon dioxide gas into a liquid, which creates that fizzy, bubbly sensation we associate with sodas and sparkling waters. It's a key factor in how these beverages appeal to us, providing not just flavor, but also that refreshing, tingling feeling on the palate. The level of carbonation can vary widely, from lightly sparkling to highly fizzy, and this impacts the overall drinking experience. When we think about product quality and consumer preference, carbonation plays a crucial role. It also influences the perception of freshness and can even affect the shelf life of a beverage. Understanding carbonation is essential because it ties into the broader themes of beverage formulation and sensory experience. Whether you're designing a new soda or a craft sparkling water, mastering carbonation helps ensure the final product hits that perfect balance of taste, texture, and sensation that consumers love. Let's talk about the alkalinity in concrete. This alkalinity primarily comes from hydroxides of calcium, sodium, and potassium that are present in the hardened cement gel. Now, when carbon dioxide from the environment permeates into concrete, it travels through the interconnected pores within the material. Once inside, CO2 reacts with those hydroxides to form carbonic acid. This chemical reaction is quite important. The carbon dioxide combines with water to create H2O3, or carbonic acid, which then reacts with calcium hydroxide, CaO2, in the concrete. This reaction produces calcium carbonate, CaCO3, and water. What's key here is that this process reduces the alkalinity of the concrete, and this phenomenon is known as carbonation of concrete. It's a natural process, but it can have significant implications for the durability of concrete structures, especially in terms of steel reinforcement corrosion. So, understanding carbonation helps us assess the longevity of concrete and plan for maintenance or protective measures accordingly. Now, let's talk about chloride attacks in marine structures. As many of you know, seawater is highly aggressive due to its chloride content, which can pose serious challenges for the durability of these structures. Chlorides tend to penetrate the concrete and reach the reinforcement, leading to corrosion over time. This process weakens the structural integrity and can result in costly repairs or even failures if not properly managed. The key point here is understanding how chloride ions infiltrate the concrete, especially through cracks or porous zones, and how they accelerate corrosion of the embedded steel. It's also important to highlight that environmental factors like temperature, humidity, and tidal cycles influence the rate of chloride ingress and corrosion progression. Connecting this to our overall theme, it underscores the importance of selecting durable materials, applying effective protective coatings, and designing structures with adequate cover and resistance features. By doing so, we can significantly mitigate the detrimental effects of chloride attacks and extend the service life of marine structures. During the use of structures, chlorides can penetrate into the concrete from various sources. The most significant of these sources is seawater, which contains a high concentration of chlorides. The rate at which chlorides penetrate depends largely on the diffusion properties of the concrete itself. Specifically, if the cover concrete has lower permeability, it takes longer for chlorides to reach the reinforcement. This means that the initiation period for corrosion is directly influenced by how permeable the cover concrete is. Chlorides pose a serious threat because they destroy the passive film that normally protects the reinforcing steel. Once this film is compromised, it can trigger the onset of steel corrosion, which can significantly weaken the structural integrity over time. So, to summarize, controlling the permeability of cover concrete is crucial in delaying chloride penetration, and consequently, extending the lifespan of reinforced concrete structures exposed to chloride-rich environments like seawater. Let's take a closer look at chloride attacks in marine structures. As you know, these structures are constantly exposed to salty seawater, which presents unique challenges for durability. Chloride ions are particularly problematic because they can penetrate protective coatings and reach the steel reinforcement. Once they reach the steel, they can initiate corrosion, which significantly weakens the structural integrity over time. This process is often insidious because it starts silently and progresses gradually. Understanding how chlorides attack helps us develop better protective strategies, such as using corrosion-resistant materials or applying specialized coatings. It's also why regular inspection and maintenance are crucial in marine environments. Essentially, chloride-induced corrosion is a key factor that influences the lifespan and safety of marine structures, and managing this threat is central to our overall approach to durable design. Soils that contain sulfates of calcium, sodium, potassium, and magnesium are actually the main source of sulfate ions in groundwater. When you find high sulfate levels in water, it's often a good indicator that magnesium and alkali sulfates are present too. Now, when sulfate ions combine with other ions like ammonium, chloride, nitrate, and carbonate, the damage they cause becomes even more severe. This is especially true for concrete structures, where sulfate attack can lead to expansion, cracking, loss of mass, and eventually disintegration. Understanding this process is crucial because sulfate attack can significantly compromise the durability of concrete, which ties into our overall theme of material durability and water chemistry impacts. Sulfate attack is a common form of deterioration that we see in concrete structures, especially those exposed to aggressive environments. It occurs when sulfates penetrate the concrete and react with components within the cement paste, leading to expansion and cracking. This process can significantly weaken the structural integrity over time. The key point to remember is that sulfates come from sources like soil, water, or even seawater, and their presence can be quite insidious because they're often hidden within the environment. When sulfates react with calcium aluminate and calcium silicate hydrates in the concrete, they produce expansive products like ettringite and gypsum, which cause internal stresses. This expansion results in cracking, spalling, and ultimately, deterioration of the concrete. It's important to consider sulfate attack in our design and material selection, especially for structures in sulfate-rich environments. Understanding this attack helps us develop more durable concrete mixes and protective measures, aligning with our overall goal of enhancing longevity and safety in concrete infrastructure. Let's talk about alkali-silica reaction, or ASR, which can cause serious problems in concrete structures. When ASR occurs, it leads to expansion and cracking, and in some cases, it can be so severe that the structure needs to be demolished. It's important to understand that ASR is actually the most common form of alkali aggregate reaction, or AAR, in concrete. There's also a less common form called alkali carbonate reaction, or ACR, but overall, both ASR and ACR are subsets of AAR. Now, what causes ASR? It happens when the hydroxyl ions in the alkaline pore solution of the cement react with reactive forms of silica present in the aggregate. These silica sources can include materials like chert, quartzite, opal, or strained quartz crystals. The reaction produces a gel that expands over time, leading to those damaging cracks we're trying to prevent. Understanding this reaction is key, because it highlights the importance of selecting appropriate aggregates and controlling the alkalinity in our concrete mixes to avoid these issues altogether. Let's talk about alkali-silica reaction, or ASR for short. This is a chemical reaction that can occur in concrete when certain silica-rich aggregates come into contact with alkali hydroxides in the cement paste. Essentially, the alkalis in the cement react with reactive silica in the aggregate, forming a gel that can absorb water and swell over time. This swelling creates internal pressures that lead to cracking and deterioration of the concrete. It's a particularly insidious issue because it often develops slowly and can be hard to detect early on. The key points to remember are that ASR can significantly compromise the durability and structural integrity of concrete structures. To prevent or mitigate ASR, proper selection of non-reactive aggregates, controlling the alkali content in the cement, and using supplementary cementitious materials are effective strategies. Understanding ASR ties into the overall theme of durability and long-term performance, emphasizing the importance of proactive measures in concrete design and maintenance. So, to understand the conditions that lead to alkali-silica reaction, or ASR, we need to look at a few key factors. First, a sufficiently high alkali content in the cement, or alkali coming from other sources, is essential. This alkali acts as a catalyst in the reaction process. Next, we need a reactive aggregate, such as chert, which contains silica that can react with those alkali ions. And finally, water is a critical component. Remember, ASR won't happen if there's no available water in the concrete, because the formation of the alkali silica gel requires water to occur. So the main conditions for ASR to take place are, first, enough alkali in the system, second, a reactive aggregate like chert, and third, the presence of water. Without all these elements, the reaction simply can't proceed. Understanding these points helps us better design durable concrete mixes and prevent future deterioration.